Hello, Srinivas. How are you?
Hello, how are you? Yeah, fine.
Good.
So I think CRN, T. Srinivas and Shivakumar, they are contemporaries in Rajan's lab. But M.V. Satyanarayana is also joining, I think.
So, Natraj, where are you nowadays?
I'm in Mysore.
Mysore.
I was from JC, so I retired in JC and I'm settled in Mysore only. Yeah.
Oh, okay.
Yeah.
So, what are you doing there, Shivakumar? How is your?
Right now, I mean, this is COVID time, right? So most of the time working from home and working on fiber optic communication and also free space optical communication, those kind of things area I'm working on.
Okay.
How about you?
Yeah. Still photonic integrated circuits, integrated optics.
Integrated optics. Okay.
All applications.
Continuing the legacy of Professor Selvarajan, right?
Selvarajan.
Yeah, he has opened up a lot of things toward like MEMS, all those things.
Yes. For some reason, after my master's, I did not work much on integrated optics. I moved more towards communications. So.
Yes. This online mechanism is a good thing that way. You need not come here. Online lectures is a good way. You need not come here.
That is the only good thing of COVID, I think. All the world is connected.
How is the COVID situation there?
Everyone
is getting vaccinated.
It's getting much better now after the vaccination. Numbers are coming down, so that's a good news.
Okay.
In India, it was really bad, right? 2 weeks ago.
Yeah. Still, now it is slightly coming down, they say. But in Bangalore, not so much still. Deaths are more now. Even though number of cases are reduced, deaths are increasing. I think it is following from the last week or 2 weeks back.
That's true.
So after another 2 weeks, this may reduce.
So still lockdown or?
Yeah. Until June 4th in Karnataka.
I see.
Srikanth, you have to call all your students.
I have called actually, even I called Calcutta University. Madhusudan? Madhusudan?
Yes, sir.
You call your, remind them.
Okay, so I think here it's already started raining. So I talked to some. They're saying like they're facing difficulties.
Okay. I think now they're dining.
Yes.
Yeah. So I think there may be some problem with the networks because.
No, sir. Now it is there is a cyclone 25th and 26th.
What is
so, yeah. So now it's already started raining from today itself.
I think Karnataka will not be affected by that cyclone.
Somewhat far away. Mangalore and all was affected recently, like
that is previous one. Earlier, Tufan, last week. Even now in Gujarat.
Yes.
So Karnataka West Coast was affected by that.
Right.
Bangalore is more towards the east, so we are thinking that new one will affect, but that has gone to Calcutta and Orissa. But the major ones come in October, November in south towards this east coast.
Right.
Usually, a lot of big ones had come in the October, November period.
That comes usually in Andhra Pradesh, right? Usually
that coast, east coast, Andhra, that corner, that what is that? Krishnapatnam area, Krishna and Godavari, that region, they hit.
I see.
So they're joining. No, many of them are joining.
Slowly they'll come.
Yes, sir. Can continue. Shivakumar, there is no problem if we start around 5:35, 5 minutes.
Sure, sure. Anytime. I'm fine. I'm open to this.
You can, by the time you can speak to CRN, then T. Srinivas, and I think MV Satyanarayan also may come.
Okay. So where is
Sulila, you can remember.
nowadays? Is it in Hassan or?
No, he's
Where
Mysore.
is Satyanarayan? Is it?
Mysore, I think.
He's in Mysore.
Mysore or Hassan?
No, he's in Mysore, sir. He's in Mysore.
After IISc, where did you go, Dr. Shivakumar?
I went to Japan.
Yeah, I know that. Yeah.
Japan, I was there for like 3 years. Then I went to Germany. I got this Humboldt Fellowship. Then after Germany, I went to join Corning.
Okay.
In New York. So finally, I moved to McMaster in Canada.
Okay.
I've been here for the past now 18 years now. So.
Oh, long time.
Long time.
Yeah, the electrical department in McMaster. What is that?
Yeah, it's called the Electrical and Computer Engineering Department.
Okay.
So I am in the head of the fiber optics group there. So.
Oh, good. There's one more person in our room who used to work with Anand. Who was that? Dr. Anand, G.V. Anand.
Who used to work with G.V. Anand? Is it a girl or?
No, boy. You were there and he was also there. I was from Kerala.
Yes, yes. I think he was. Who was it?
No, he was not with G.V. Anand. Sadasivan.
Oh, Sadashivan, right.
No, not
he was not
Sadashivan.
With. Yes.
He was.
Reddy.
He was with
Yes,
Professor Silvarajan,
he
but
was
working
with,
more
not
with
with Reddy. One more digital signal processing professor. I forgot his name. His room was next to Reddy's room. Right now he is in Singapore.
Yeah, I know. I met him recently, some time ago. Not recently, some 2-3 years ago.
Right. Was it something like Narayan or something? I forgot his name.
No, I'll tell you. Yelumalai was there.
No, maybe
he was also not.
Maybe Narayan. I'm not sure. He was from Kerala.
That is, his name is Sadashivan. Yeah, he was my roommate.
I know very well.
Yeah.
And then Yelumalai was there at that time. Kerala was there. Pillai was there. SP Pillai before us, slightly before us.
Pillai was there, right? Indukumar, you know where Indukumar is?
No.
Yeah.
Where is he? He was in Singapore too, I thought, right?
Yes. Then what was that fellow's name? Some of our fellows are there here. Mahadev Lad is there here in Bangalore.
He goes to China frequently, right, Lad?
Yeah. He was going here and there. He was in Japan for a long time.
Right. Yeah. I am in touch with him sometimes. Occasionally we send emails.
Then Tyagaraj was there. Tyagaraj also is here.
Which Tyagaraj?
One fellow Tyagaraj was there. His mother was a Carnatic music singer.
Okay.
He did ME.
Oh, okay.
With Professor
I don't know him. I think so. About a few months ago, I got a call from Anna Chelvi, so we chatted for some time. Yes.
I wanted to call her actually. Okay. Recently, I got this number from Jaggu.
Okay.
Jaggu, Swaminathan and all, they had come later.
I see.
End of the last century.
So Nataraj, do you remember Shankar?
Yeah. He was there. Yes.
And where is he now?
No idea, but
no idea. Okay.
Yes, sir. Natarajan, you are in touch, Shivakumar.
With whom?
Natarajan. Yes, sir. Natarajan. He was there towards the end of last century. With Professor
End of last century.
Swaminathan, Natarajan, they were there.
Okay.
I think you may not have been in touch.
I am not in touch with them, so.
I remember Professor K. Tyagarajan from Delhi was your PhD examiner.
Right.
Professor Selvarajan had asked me to go to airport and pick him up.
Oh.
Yeah.
Yeah, we had that conference, right? First conference, Photonist conference back in
94, I think.
Next year we need to conduct that.
First one was in 1991, I think.
Yes, correct.
So that time we did a lot of work bringing people from the airport and running around.
Cleaning up the OHPs.
Yeah, very much.
We didn't have PowerPoint those days, right? So
OHP was the in thing.
You have to clean with trichloroethylene and all that, and write again on the same OHP.
But by 94, we could do photocopying on transparencies. That was a bit better.
Yes.
Instead of writing, we could photocopy images and pictures onto the transparency.
So when did we get PowerPoint? 97, 96 time frame.
Even 95. 95 was there. Yeah. By 95, it was there. As soon as Windows was launched, somewhere in August, we could.
But then we used to print out onto the OHP from PPT and then use in the beginning.
So got so much used it to OHP. So
95 OHP. Majority of it was OHP. Right, it faded away completely. It is an antique piece now. OHP. I think you can share your screen, Shivakumar.
Okay, let me see how to share.
Professor MVS has come.
Oh,
hello, Professor Satyanarayan. How are you?
The MVS has to unmute.
Yes, I think he's on mute.
Sir, good evening, sir. MVS, sir.
You can please show the video also.
He doesn't know that he's muted, I think so.
Let us call him otherwise.
So I'll call him and tell that unmute. By that,
should I should I wait?
In the meantime, you can share your slide.
Yeah, he has unmuted.
Now he's unmuted?
Yeah.
Okay. You can call him, sir.
Call him also,
Sir,
no
MVS, sir.
So, Professor MVS, Dr. Shivakumar is here.
Hello, Professor Satyanarayan. How are you?
He is unmuted.
I don't know. I cannot hear him.
Maybe volume is low or something. Hello.
Hello.
Yeah, now we are able to see him. So, Satyana. You can pin on him. You can see him.
Yeah, I can see him.
Yeah, you can pin.
Yeah.
I pin?
Pin. Yeah, I mean that pin like symbol. If you press, you can see him.
Hello. He is not able to hear you. He is not able to hear, it seems, sir.
He's not able to hear, I think. Yeah.
Then you
I
call
think
him.
he's unmuted also.
Unmuted, but he's not able to hear. I don't know his.
1 second, I'll comment. Yeah. Hello. Hello, sir. ಕೇಳಿಸ್ತಾ ಇಲ್ವಾ?
ಕೇಳಿಸ್ತಾ ಇದೆ ಹೇಳಿ. ಇಲ್ಲ
ಶಿವಕುಮಾರ್ ನಿಮ್ಮನ್ನು ಕೇಳ್ತಾ ಇದ್ದಾನೆ.
ಆಯ್ತು ಮಾತಾಡ್ತೀನಿ ಬಿಡ ಆಮೇಲೆ.
ಓಕೆ ಸರ್. ನಾವು ಇದಷ್ಟೇ ಹಲೋ ಸರ್. ಶ್ರೀನಿವಾಸ್ ಅಂಡ್ ಶಿವಕುಮಾರ್ CR ನಟರಾಜ್ ನಿಮ್ಮನ್ನು ಕೇಳಿದ್ರು ಅದಕ್ಕೆನಾ ಸರ್? ಓಕೆ. You can speak, sir.
Hello, Professor Satyanarayan. ಹೇಗಿದ್ದೀರಾ?
ಹಲೋ.
ಕೇಳ್ತಾ ಇದೆಯಾ?
I think he's okay. I think Shivakumar, he told that let us speak after.
The speaker is very low,
Sure.
I think.
Okay, I think volume is pretty low.
I think now you can Start present. Shivakumar.
Should I start my talk?
Yeah, you can start. Then later on, we can discuss.
Okay. Okay. Good morning, or is it probably good evening?
Have you?
Good morning for me. So anyway,
Shivakumar, 1 second. I just try to do. So I welcome Dr. Shivakumar for this talk. I welcome, and also I welcome Dr. M.V. Satyanarayana, C.R. Natra, Dr. T. Srinivas, and I request Pooja to introduce today's speaker. Pooja?
Yes, sir.
Please introduce today's speaker.
Good evening, everyone.
Let's start.
Good evening, everyone. I am Pooja HM, Student Chair of IEEE MCE Student Branch. It's a great pleasure for me to introduce our today's speaker, Dr. Shivakumar, sir. Professor Shivakumar received his MS in 1990 and PhD degrees in Electrical Communication Engineering in 1994 from IISc, India, and another PhD degree in Communications Engineering in 1997 from Osaka University, Japan. He worked as a postdoctoral fellow at the University of Jena, Germany, supported by Alexander von Humboldt Foundation from 1997 to 1998. He also worked at Incorporated, New York, as a senior research scientist from 1998 to 2001, as a supervisor from 2001 to 2002, and then as a project leader from 2002 to 2003. Currently, he is a professor at Department of Electrical and Computer Engineering, McMaster University, Canada. In 2001, he obtained an Outstanding Individual Contributor Award from Corning Incorporated, one of the world's leading innovators in material science, a Circle of Excellence Award from Photonic Spectra, and an R&D 100 Award by R&D Magazine for the product Metrocore. His current research interests include fiber optic and wireless optical communication, solitons, nonlinear optics, photonic devices, and general relativity. Dr. Kumar is also a fellow of the Optical Society of America. He has published about 90 papers in referred journals and 7 book chapters. He authored a book on fiber optic communications, edited a book on nonlinear fiber optics, and holds 8 US patents in the field of optical transmission systems. With this brief introduction, I welcome Professor Shivakumar, sir, to deliver his talk.
Thank you very much for the kind introduction. And I would like to thank Professor Shrikant for inviting me to give this talk. So the title of my talk today is Compensation of Impairments in Fiber Optic Systems. The outline of my talk is as follows. First, I will discuss the basics of intra-channel and inter-channel nonlinear impairment. And then I will discuss how to compensate for them. There are 2 techniques for compensation: digital back propagation, or DBP, and optical back propagation, or OBP. The OBP can further be divided into 2 types: lumped OBP and distributed OBP. Finally, I'll compare these techniques in terms of performance and complexity. This figure shows the inter-channel or classical Fourier mixing. So consider a WDM system with 3 channels centered at frequencies F1, F2, and F3. I'm not sure how many of you are familiar with the WDM system. WDM stands for wavelength division multiplex system. So in which we are going to have each channel as a certain frequency. So we have channel 1, for example, at frequency f1, or correspondingly an equivalent wavelength. f2 is another channel with a different wavelength like that. So we will multiplex all those channels of different wavelengths together. So that's what is the meaning of the wavelength division multiplexing means. So suppose we have channels like this centered at f1, f2, f3. Note that the fiber is a nonlinear medium. As a result, they mix. So there's a nonlinear interaction happening, and they lead to the sidebands, the Fourier mixing sidebands at f1 plus f2 minus f3. It's all happening in the frequency domain, and also one more sideband at f2 plus f3 minus f4. If we are in a typical WDM system, we'll have many channels. Think that there's a fourth channel, say channel 1, 2, 3. There's a fourth channel here, signal channel, on which this Fourier mixing sideband falls. So this would act as noise, leading to performance degradation. So this Fourier mixing is actually causes performance penalties. Now let us consider, this is called the inter-channel because it's happening between channels. There's also something known as intra-channel Fourier mixing or I-Fourier mixing. So consider a single channel system, and we have got, let us say that we are sending bits 1, 0, 1, 0, something like that. Let's say there are 3 bits, I'll say bit 1, 1, 1, for example. We have got pulses to represent bits. And nonlinear interaction happens within the channel now. That's why it's called intra-channel. So nonlinear interaction of the 3 pulses centered at T1, T2, and T3 of the same channel produces echo pulses on both sides. So there's an echo pulse here at T1 plus T2 minus T3. And also there's an echo pulse in this location, T2 plus T3 minus T1. And if there's a signal pulse here, the echo pulse acts as noise, leading to performance degradation, just like the case of the inter-channel. So these two are quite similar. Only difference here is that the x-axis is here time, here is the x-axis the frequency. All right, so next I will discuss more on the intra-channel Fourier mixing. So this figure shows the power, signal power as a function of time, and it shows the nonlinear interaction between 3 signal pulses. Here the dotted line is the input to the fiber optic system, and the solid line is the output. As you can see, their pulse peaks, they fluctuate because of the nonlinear interaction. Not only that, they produce echo pulses on both sides. So if there is a signal pulse here, it would act as a noise on that. You cannot see in this example this echo pulse very clearly because it's a linear plot. Next, I will show it in the log plot, a 3D simulation. And here we have got 3 signal pulses launched, and the z-axis is the power, x-axis is time, and the y-axis is the distance in the fiber optic link. So the nonlinear interaction among these 3 signal pulses produces the echo pulse on both sides, as I mentioned before. I'll call it the first order echo pulse. And the nonlinear interaction among the signal pulse and the first order echo pulse produces second order echo pulse. So however, the question of, okay, so the second order echo pulse amplitude is very small, it's around minus 100 dBm, so which can be typically ignored. So let me now discuss the difference between intra-channel nonlinear impairments and inter-channel nonlinear impairments. So consider a WDM system with say 5 channels, and consider the central channel, say channel 3, and a central pulse here. Its nonlinear interaction with the pulses of the same channel as shown here. It's known as the intra-channel nonlinear impairment. The one example I mentioned, intra-channel Fourier mixing, is an example for the intra-channel nonlinear impairment. And the interaction of this signal pulse with the pulses of the other channels, that is known as inter-channel nonlinear impairment. The classical Fourier mixing is an example for the inter-channel nonlinear impairments. I would like to point out that I'm going to consider two schemes. One is the digital back propagation, other one is the optical back propagation. In the case of the digital back propagation, it can compensate only for intra-channel nonlinear impairments. It cannot compensate for the inter-channel nonlinear impairments, whereas the optical back propagation can compensate for both. So first, let us look at the digital back propagation, or DBP. So consider a transmission link consisting of N fibers and N amplifiers. Each fiber is characterized by three parameters: the fiber loss, alpha, dispersion, beta 2, and nonlinear coefficient, gamma. So this is the fiber optic link, and its output falls on the coherent receiver, which consists of balanced photodetectors, analog to digital converter, and digital signal processing unit. And the digital back propagation is carried out inside the DSP chip. Nowadays, coherent receiver is quite advanced, and we have got this DSP operating at 28 gigabaud. That has become very standard. And this figure shows the block diagram of the digital back propagation that's happening inside the DSP chip. So we have this received signal in the digital form, and we have here inside the DSP chip something we call the virtual fiber. Virtual fiber is characterized by, again, the three parameters: negative alpha, that's the negative loss, negative dispersion, and negative nonlinear coefficient. This negative loss means gain. So that means that the power in this fiber, virtual fiber, increases exponentially with distance. Whereas in the real fiber, it decreases exponentially with distance. So it should be exactly opposite of whatever we do in the real propagation. In the back propagation, we have to do the opposite. So we have got amplifiers here, series of amplifiers, and we have got series of loss elements here. For example, if this amplifier provides 25 dB gain, then this loss element should provide 25 dB loss. It's exactly inverse of what it happens. So this virtual fiber compensates for any distortion caused by the last span of the real link. The second virtual fiber would compensate for the distortions caused by the last but one, and so on. And this nth fiber compensates for the first fiber's distortion, and so on. So this virtual fiber optic link, end of the virtual fiber optic link, is the same as the input to the real fiber optic link if there is no noise in the system. If there is some noise, there is some penalty, but it's not major. So you may ask how we realize this virtual fiber on DSP unit. So what we do for that, we have to solve the nonlinear Schrodinger equation in real time. So I will explain that in the next slide. So signal propagation in a fiber is described by the well-known nonlinear Schrodinger equation. I will not go into the details of that. So here d of t is the dispersion operator, beta 2 is the dispersion coefficient here, and n of t is the nonlinear operator, with gamma and alpha being, the gamma is the nonlinear coefficient, alpha is the loss coefficient. So let us pretend that they are not really operators. They just think that they are variables. So then this is the first order differential equation, which can be easily solved, and its formal solution can be written in this form. Here QT0 being the signal at the input of the fiber optic link, and this is the QT comma delta Z is the signal at some distance delta Z, and this whole thing, I call it the propagation operator M. So just to give an example, if you look at this fiber optic link, let us say that QT comma 0 is the input signal to this link. Let us say that this length is delta Z. So QT delta Z is the output of the link. So this M, the propagation operator, corresponds to the fiber optic link, propagation in the link. So that's what this operator M is about. Now let us look at the inverse problem. Suppose we know the output of the link, and we want to find out what the input is. So that is the inverse problem. So what we do for that, we operate M inverse on both sides of this equation. We operate M inverse on this, and if you operate M inverse on m inverse times m in the operator or the matrix equation, that gives us the identity operator. So that's basically nothing there. So m inverse on q, t comma delta z gives us qt0. So that's how we get back our original signal. And that's what we are doing in the digital backpropagation. So we have the received signal in the digital form here, and we operate m inverse using these virtual fibers on the received signal to get back our original signal. The next question is, how do we synthesize this inverse operator, m inverse? To do that, let us note that this propagation operator m is of the form e to power of x here, where x is this quantity here. And e to power of x times e to power of minus x is the identity operator for any operator x. So you can easily see that we can synthesize this m inverse as e to power of minus x. So that's minus dt and minus nt here, sitting in the exponent here. So minus dt means dt is minus beta 2. So minus dt is plus beta 2. And nt has got plus gamma. So minus nt means minus gamma and minus alpha. So therefore, if we can realize a virtual fiber with minus alpha, minus beta 2, and minus gamma, that would exactly compensate for the distortions caused by the fiber. So that is the essence of digital backpropagation. So this also gives us the math behind it. All right. It looks good, everything on paper, but there are some practical issues with the digital backpropagation. It requires extensive computational resources. We need to solve the nonlinear Schrodinger equation. It's a nonlinear equation. It's hard to, it takes a lot of time in real time if you have to realize it on FPGAs, and requires many 50 needs to be done over a period of 100 picoseconds. So that is the problem. And other main problem is that digital backpropagation cannot compensate for inter-channel nonlinear impairments in optical networks. The receiver at the current node does not have access to the channels that were dropped in the previous nodes, which I will come back to this point later when I talk about optical networks. And currently, digital backpropagation can provide a performance improvement of only 1 dB by compensating only intra-channel nonlinear impairments. So next, let us look at the optical backpropagation, or OBP. So instead of virtual fibers, we could think of using real fibers with negative dispersion and negative nonlinear coefficients. Unfortunately, fibers with negative nonlinear coefficients are not available. But the same results can be obtained if the output of the fiber optic link is passed through an optical phase conjugator. So we have this fiber optic link here, shown here. Its output is, I will call it Q of T comma L. And after the OPC, we get this conjugated signal, I'll say Q star T comma L here, which passes through the real fiber, which is identical to the transmission fiber. I call this fiber the OBP fiber, that is the optical backpropagation fiber. And this entire thing, I'll call it the OBP module. It can be shown that the output of the OBP module is complex conjugate of the input. That's Q star T comma 0 here, which is the complex conjugate of the input QT0. And to recover the input, we perform a phase conjugation in the digital or optical domain again, using one more optical phase conjugation, for example, or we can do it in the digital domain easily. So that's how we get back our signal. The issue is that if the transmission fiber is 80 km long, the fiber in the OBP module should also be 80 km long. I said that this fiber should be identical to the transmission fiber. We don't want to put an extra 80 km long fiber at the receiver, so that's not very practical. What we would like to do is that we wish to make this optical backpropagation module only a few meters long. We want to put some black box, a small black box at the receiver, which can undo the fiber distortions. So in order to do that, we approximate the fiber propagation by a split step technique. It's a well-known split step technique in which we have as shown in this equation, the left-hand side is the propagation operator in which dispersion and nonlinearity act simultaneously here. Here D is the dispersion operator and N is the nonlinear operator on the conjugated signal. And on the right-hand side, first we operate only the dispersion on the conjugated signal, and then we operate the nonlinearity separately. So this is the well-known technique to solve the nonlinear Schrodinger equation. Also, sometimes it's also called the beam propagation method in integrated optics, very similar. So note that here, let me call it x, let me call it y. It's basically e to the power of x plus y here. E to the power of x plus y, we are approximating as e to the power of x times e to the power of y. Although it's exactly equal, e to the power of x plus y is e to the power of x times e to the power of y for the variables, it's not, it's only approximately equal for the operators. Its approximation is good if the step size delta z is small. So later I will discuss the impact of this large step size, if you take, on the performance of the back propagation. So we are actually using this for the propagation itself, not for solving the NLSE. I will illustrate that later. All right, so now let us see how we use this approximation and see how we realize the back propagation. So dispersion operator can be realized using a highly dispersive fiber. I'll call it HDF, or fiber Bragg grating, FPG. Its purpose is to provide the accumulated dispersion that is the same as that of the transmission fiber. Nonlinear operator can be realized using a highly nonlinear fiber. Its purpose is to provide the nonlinear phase shift that is the same as that of the transmission fiber. For example, to compensate the dispersion of 80-kilometer long Corning metro core fiber, we need only a few centimeter long fiber Bragg grating. And to compensate the nonlinearity of the fiber, we need only a few meters of highly nonlinear fiber. So it's possible that we don't need a 80-kilometer long OBP fiber. We can replace it by few meters long highly nonlinear fiber and few centimeter long fiber Bragg grating. So that's the idea. I will show this scheme. I will call it the lumped OBP. Later I will discuss about the distributed OBP also. So here I'll discuss two schemes. First, let me give the big picture. So we have the transmission link consisting of n spans of fibers and amplifiers. And at the end of the link, we introduce this OBP module, and then its output goes to the receiver. In scheme 1, I choose the step size delta z is equal to amplifier spacing. I will explain it in this slide, what it means. So we have the link output, that's whatever this one coming into this OBP module, consisting of the optical phase conjugator and then amplifier and HDF. HDF stands for the highly dispersive fiber. And this HDF compensates for the dispersion of the last span, and HNLF compensates for the nonlinearity of the last span, and HDF2 and HNLF of the second set of HDF and HNLF compensates for the last but one span of the fiber optic link, and so on. This is the scheme 1. In scheme 2, what we do is that first set of HDF and HNLF compensates for the second half of the last span, and second set of HDF and HNLF compensates for the first half of the last span, and so on. So we have got even the smaller step size here for the back propagation. So theoretically speaking, we should get much better performance. However, in practice, we find that it does not bring a huge advantage, as I will show in the next slides. So before that, let me talk about the one more technique known as midpoint optical phase conjugation. It has been known for a long time. It was introduced by Professor Yariv back in the 80s. So what you do is that we have got, it is similar to this figure. We have got the transmission link, say 1,000-kilometer link. After 500 kilometer, you put an OPC. In the next 500 kilometers, you have the actual fiber optic link, which would compensate for the link before the OPC. That's what is known as the midpoint OPC. So the technique that we have proposed is similar to that, but there are some differences. So in this case, the OPC is placed at the middle of the link. The second half of the link compensates for the nonlinearity of the first half, as I explained. In the case of optical back propagation, we introduce a dedicated photonic system. It's built to compensate for the nonlinear impairment. So in the case of the midpoint OPC, there is an issue that there should be a power symmetry about the OPC location, which cannot be satisfied in practice, because in North America, amplifier spacings are random, leading to power asymmetry. So we could have like one amplifier after 80 kilometers, next one maybe after 125 kilometers. So there is a lot of randomness in the amplifier spacing, and under that condition, midpoint OPC does not work. So that is the problem. Optical back propagation can work under that condition, but the problem with the OBP is that the photonic devices of the OBP module add noise, causing performance degradation. So that is the issue with the OBP. So let us now look at the performance results. This figure shows the bit error rate as a function of the maximum achievable distance in a fiber optic link, and the maximum distance that we can get in the link without optical back propagation, but with dispersion compensation, is limited to about 300 kilometers for QAM32 at the BER of 2.1 times 10 to the power of -3. That is the FEC limit, as I have shown here in this slide. So if you use midpoint OPC, and assuming everything is nice, like perfect symmetry, amplifiers are perfectly spaced, and assume that under ideal condition, using midpoint OPC, the maximum reach can be extended to about 900 kilometers. And if you use the scheme 1 that I mentioned in the previous slide here, scheme 1 with step size equal to amplifier spacing, in that case that is shown in this figure here, we can increase the reach to about 1350 kilometers. And if you use the step size of LEA over 2, that is the scheme 2, it can be increased to about 1450 kilometers. So that's about 100 kilometers you can get an performance improvement using the scheme 2. Scheme 2 is this one. So the improvement we get is marginal, only roughly like 100 kilometer improvement in the reach. Although theoretically we would expect a much larger improvement, the reduction in improvement is due to the fact that when we add more photonic devices compared to here, the photonic devices are doubled here. They introduce loss. Each photonic device introduces loss. In addition, there are some insertion losses because of these photonic devices. So because of these additional losses, we have to increase the gain of the amplifier, which adds more noise. As a result, scheme 2 has more noise added than scheme 1. So that is what is causing the performance degradation. So we get a slight improvement, but not a whole lot. Nevertheless, if you compare the case without OBP, it's only 300 kilometers, which can be increased to roughly about 1500 kilometers using the scheme 2. So that's about 5-fold increase in the reach. That's a significant. So there have been some experimental validation of our proposed idea of using lumped OBP. Kaminsky et al. Performed the all optical back propagation experiment, in which the transmission fiber is Corning leaf, and they used the OBP module consisting of highly nonlinear fiber Bragg rating, and 10 kilometers of standard single mode fiber, and reported about 2 dB improvement in SNR using this optical back propagation for 7-channel WDM system at 16 gigabaud per channel, and 16 QAM was used. So they also did another experiment, optical back propagation experiment using dispersion shifted fiber, and reported about 3 dB improvement in SNR with dual polarized 16 ohm. So lumped OBP, although it gives performance improvement, there are some issues, because as I mentioned before, ideally this should give much higher performance improvement, but adding these photonic devices is what limiting us to increase the performance further. as I've written here. So to avoid this problem, we would like to introduce a single fiber or device in the OBP module. If you introduce a single fiber, we don't need to worry about the insertion loss and such issues. So this desired fiber or device should be short and should compensate for dispersive and nonlinear effects of the transmission fiber exactly. A dispersion decreasing fiber or DDF is found to meet these requirements. So this is the distributed OBP I'm saying, using dispersion decreasing fiber. So we have got, consider a WDM system with M channels. So we have got M transmitters with different wavelengths. They're all multiplexed using a WDM mux here, and this combined signal passes through the fiber optic link consisting of n spans of fibers and amplifiers. And at the end of the link, we introduce an OBP module consisting of a preamplifier, optical phase conjugator, band pass filter, dispersion decreasing fiber, and an amplifier, and such units here. So at the end of the optical back propagation module, we have the WDM demux, and the signals go to their respective receivers. So the OBP scheme in this case provides the exact compensation for nonlinear impairments of all the channels of a WDM system. It's not only for one channel, it is compatible with WDM system. So we have derived an analytical expression for the dispersion profile of the dispersion decreasing fiber in this form. You can look at this paper for more details. So the dispersion profile is so chosen that the dispersion and nonlinearity of the transmission fiber are cancelled exactly. This figure shows the dispersion profiles here. So for this case, figure A, for the G is equal to 1.0. So G is 1 means there is no preamplifier. So in fact, this dispersion profile depends on the gain G of the preamplifier shown here. So if G is 1 means that there is no preamplifier. In that case, the length of the DDF is quite long, like 20 kilometers long. But if you introduce a preamplifier, even with a very small gain, like G is equal to 1.5, length of the DDF now is only up to 9 kilometers. So that's the typical length of the dispersion compensating fiber used in dispersion managed systems. Here the initial dispersion of this DDF is 130 picosecond square per kilometer, which is the same as that of the commercially available DCF. The only difference between the DCF and DDF is that in the case of the DCF, the dispersion is constant as a function of length, going to be 130 picosecond square per kilometer throughout the length. Here in this DDF, it decreases from 130 to about 8. So this particular dispersion variation is chosen so that the nonlinearity is compensated exactly. So now let me show the results. So we have the bit error rate as a function of the maximum achievable transmission distance for 28 gigabaud 32 QAM 5-channel WDM system. For the linear, if we compensate only dispersion, the maximum distance is about 300 kilometers. So that is the FEC limit up to 0.1 times 10 to the power minus 3. If we use mid OPC, it does not bring huge advantage. It gives only maybe another 100 kilometers improvement, like maybe 400 or 350, something around that. And if we use the digital back propagation with very small step size, say 3 kilometers or so, then the transmission reach can be increased to about 1600 kilometers. And if we use the optical back propagation with dispersion decreasing fiber, we can get up to 2500 kilometer reach. So although I said here DBP with step size of 3 kilometers, this is not practical for WDM system because it requires too many number of FFT operations. 3 kilometers every time corresponding to 3 kilometers, we should have FFTs done. FFT and IFFT should be done. So like that, if you are going to have like 5000 kilometer reach overall system, then we have to have like thousands of FFTs should be done, which is not very practical. And also, that's why it's currently DBP is used in some of the systems. It's limited only for single channel system. It cannot be used for WDM systems. In contrast, optical backpropagation can be used for WDM systems as well. So in optical networks, there are two possible schemes. Let's consider the scheme A. It's between node J and node J plus 1. We have a transmission fiber, then optical phase conjugator, then dispersion decreasing fiber, and inline amplifier, and such units between two nodes of a network. And this dispersion decreasing fiber and optical phase conjugator, they are placed in the amplifier side, along with the inline amplifier. So that's why I'll call it the inline OBP. In scheme B, between node J and node J plus 1, we have the transmission fiber, inline amplifier, and such units. And at the end of the link, we introduce the OBP unit. So that is the OPC and dispersion decreasing fiber. So this OBP is placed at each node. So that's why I call it the node OBP. In both schemes, nonlinear distortions are fully compensated and system is effectively linear between node J and node J plus 1. So let me explain. In contrast, DBP at node J plus 1 cannot compensate for inter-channel nonlinear impairment due to another channel that is dropped at node J. I will explain that further in this slide. Let us consider a WDM system. Let's say consider only two channels of a WDM system with the channel 1 and channel 2 co-propagating between node 1 and node 2. And channel 2 writes nonlinear distortion on channel 1 and is dropped at node 2. So it's dropped here. Then channel 1 continues further from node 2 to node 3, and channel 1 is dropped at node 3. And then we have a receiver for this channel 1. And then we have the digital signal processing and unit, and then we have the DBP there in the receiver there. And the problem is that for the DBP, at this node 3, it does not have information on channel 2. Channel 2 is dropped in node 2. It's in some other location. So to fully invert the channel or to fully compensate for the nonlinearity, the DBP should have the information on the channel 2, but it does not have access to that. As a result, digital backpropagation cannot compensate for nonlinear distortion due to channel 2 on channel 1. In contrast, optical backpropagation scheme that we have devised, we are going to introduce the optical backpropagation module just before the node, so which has access to all the WDM channels. Therefore, we have no worries about something is dropped and which is not compensating. So at every node, we have this optical backpropagation module, so that problem does not arise. Right. This figure shows the Q factor as a function of, launch power per channel for QAM64 5-channel WDM network. Q factor stands for quality factor. So the large Q factor means better performance. So the general feature of all this figure is that when the launch power is low, the Q factor increases with the launch power here. And after certain optimum point, Q factor starts decreasing with launch power. So initially, the Q factor increases with launch power because the higher the launch power means the higher SNR is going to be high, and therefore the Q factor increases. But after certain optimum point, Q factor decreases because the nonlinearity kicks in. So this is the linear region, this is the nonlinear region. So nonlinearity causes distortion, and which increases with the launch power, and the Q factor, the performance starts degrading. So if the optimum points moves from left to the right for specific scheme, that means that this scheme is more effective in mitigating the nonlinear impairments. So let's start with the linear compensation. The maximum Q factor is about 1.9 dB, which is slightly increased to about 2.2 dB using digital backpropagation. So it just gives like 0.3 dB improvement only. dB does not help much for the networks, although it gives significant improvements theoretically for the point-to-point systems. Then further, if I use the OBP scheme A, so that was the node OBP, we can get an maximum Q factor is like 9 dB. And if you use inline OBP, the maximum Q factor is about 11 dB. So optical backpropagation outperforms the digital backpropagation by about 9 dB. So distributed OBP using DDF, there are some issues too. It's hard to fabricate a fiber with its dispersion varying. One of my friends from Corning, in fact, fabricated this fiber, and we did some transmission experiments using this DDF and found that the performance improvement is only 3 dB. Well, theoretically, simulations showed much higher improvement in the performance. So this discrepancy is due to the fact that optical backpropagation is sensitive to the dispersion variations of the dispersion decreasing fiber. If the target specs are not met, OBP will not provide performance improvements. So we also did some OTDR measurements, and that revealed that the measured dispersion profile was quite different from the target profile. So when we measured with the OTDR measurement, we found the profile. This is what the profile we used to fabricate the fiber. But once it was fabricated, it was not like this. It was having some fluctuations, something like this, around this. These fluctuations were large, and that was causing performance degradation. That's what we found. So still we are working on it to make a better fiber, but that's still work in progress. But we didn't want to give up, and we tried another scheme for optical backpropagation using Raman pumped dispersion compensating fiber. So this scheme is similar to the previous scheme, but let me explain again. So we have the transmission fiber in which the power decreases exponentially with distance, and then we introduce the optical backpropagation module here, consisting of optical phase conjugator, preamplifier, dispersion compensating fiber here. The signal in dispersion, or DCF, the signal in DCF is amplified by a forward pump or backward pump or bidirectional pumping. So then finally it goes to the receiver. So it is just like the previous scheme of using dispersion decreasing fiber, except that we replace the dispersion decreasing fiber by the Raman pumped DCF. So in the next slides, we will investigate various pumping schemes like forward pumping, backward pumping, and all. And you can also look at our paper for more details. And note that the power decreases exponentially in the transmission fiber. And for the perfect compensation of the nonlinearity, it is desired that the power should increase exponentially with distance. If you recall, I talked about the digital backpropagation, in which we have the virtual fibers, and I said that the power in the virtual fiber should increase exponentially because the negative loss coefficient minus alpha. So we want the exactly same thing. The difference is that instead of the virtual fiber, we want to use the real fiber. So this DCF with Raman pumping would help us to make this power growth nearly exponential, although not exactly. I will explain that in the next slides. So let's review the different pumping schemes first. So Raman amplifier with forward pumping. So we have got the signal that should be amplified, and a Raman pump. We combine them using a fiber coupler, and it goes to the fiber. And inside the fiber, the Raman pump transfers power to the signal. As a result, the signal is amplified and the pump is attenuated. So we get this amplified signal here like this. So this figure shows the evolution of signal power in Raman amplifier. So here the signal power in dBm as a function of the fiber length. The initial power launched to this Raman amplifier, the input power in this example is like around -6 dBm. And the power increases towards 0 dBm. And then it starts decreasing because the loss in the fiber takes over the gain. And this is in the presence of the Raman pump. If there is no Raman pump, signal power decreases exponentially with distance. Although I showed a straight line because it is the log unit here. So it looks like a straight line. Otherwise, it actually decreases exponentially with distance in the absence of the pump. In the presence of the pump, we get some gain. So it was -6 and it's close to 0. So we get roughly 6 dB gain if we choose the length to be around 20 kilometers. This is the forward pumping. Let me talk about the backward pumping here. So in this case, the pump is counter propagating. So we have the signal is propagating forward in the fiber, and the Raman pump is introduced through a coupler to the fiber, and the Raman pump propagates backward, and the pump transfers energy to the signal, and we get the amplified signal coming out here. And what we have done for our OBP purpose, we used the bidirectional pumping, which means that we have the backward pump like this, as well as a forward pump from here. So that is the bidirectional pumping. So bidirectional pumping, in that case, the signal power evaluation in the DCF is given by this equation here. Here PP0 plus is the input power of the forward pump, and PP0 minus is the input power of the backward pump, and Z effective plus and Z effective minus are the effective distances. And here alpha S is the loss coefficient of the fiber at the signal wavelength, and PS of 0 is the input power to this Raman amplifier. So we did some pump power optimization for the case of the bidirectional Raman pumping. So consider the following optimization problem, where we have we define zeta as the ratio of the pump power, the backward pump power to the forward pump power. And we define the error as the integral of PS ideal minus PS. Here PS ideal is the ideal power profile, that is the exponential profile I was mentioning before. And PS is the signal power profile using the bidirectional pumping for a specific value of this ratio zeta. So this error depends on this ratio, and it's plotted here. As we can see, error becomes minimum when this ratio is unity. That corresponds to the case of the backward pump power and forward pump power being equal. So that's what the condition we use for our simulations. Next, in the next figure. So here, the green curve shows the power profile inside the DCF, the power evaluation power profile inside the DCF, which is nothing but the ideal exponential profile required for exact compensation of dispersion and nonlinearity. So that is the green curve, and the blue curve shows the case of the backward pumping, and the pink one shows the case of the forward pumping, and the star shows the case of the bidirectional pumping. You can see that the bidirectional pumping nearly matches that of the exponential profile or the ideal OBP profile, and therefore we should expect that bidirectional pumping would outperform the forward pumping or backward pumping. So whatever the deficiencies of the forward pumping, that is compensated by the backward pumping, and when we do bidirectional, we get nearly ideal exponential profile. So we consider two configurations. In configuration A, we have this OBP module that follows the transmission fiber. In configuration B, we have this OBP module that precedes the transmission fiber. And it turns out that the configuration B is slightly better than configuration A. And here we compare various pumping schemes. This figure shows the Q factor as a function of launch power per channel. Let's start with the single channel DBP. That's shown by this figure, this one with the square and dotted lines. So single channel DBP, I mean that central channel is demultiplex and the DBP is applied only to the central channel. And in this case, we see that the maximum Q factor is actually for a 5-channel WDM system with the distance of 5,000 kilometers. And the maximum Q factor with single channel DBP is about 2.5 dB. And if you use forward or backward pumping, here shown in this figure, this one, I hope you can see my cursor. The performance it slightly improves, like it becomes like 3.2 dB. So we get a performance advantage of about 0.7 dB using forward or backward pumping. And if we use wideband DBP, it's a point-to-point system, so we can use wideband DBP. Wideband DBP, I mean the DBP is applied to all channels of the WDM system. That time the maximum Q factor is 5 dB. And if we use the bidirectional pumping, as shown here, the Q factor, maximum Q factor is about 10 dB. So therefore, if we compare it with single channel DBP, which is around 2.5 dB, it goes to 10 dB. So we get about 7.5 dB improvement in Q factor using bidirectional pumping. And also we compared the maximum achievable reach. So bit error rate as a function of the maximum achievable reach at the efficiency limit of 2.1 times 10 to the power minus 3. Using single channel DBP, we get about 500 kilometers reach, and which can be increased to about 1,150 kilometers using forward pumping or backward pumping, which can be further increased to about 2,000 kilometers using the wideband DBP. And using bidirectional pumping configuration B, we get about 6,500 kilometers. So if I compare the single channel DBP, it's 500, it's 6,500 kilometers. So it's more than 10-fold increase in the transmission reach using bidirectional pumping, which is significant performance improvement using the bidirectional pumping based OBP. So I'll conclude my talk. For WDM systems, digital techniques are not effective due to the following reasons. For point-to-point systems, computational cost is extensive since the step size needs to be very small. For optical networks, receiver at a node does not have access to other WDM channels dropped at other nodes, and hence inter-channel nonlinear impairments cannot be compensated for. In contrast, optical backpropagation can provide compensation of nonlinear impairments in WDM networks in real time. Lumped OBP provides 2 to 3 dB improvements in performance. To enhance the improvement, we need to add more photonic devices that leads to performance penalty. Distributed OBP using dispersion decreasing fiber provides significant performance improvement, but it's hard to fabricate this kind of DDF. Still, this is the work in progress. Distributed OBP using Raman pumped DCF looks quite promising. The bidirectional pumping scheme provides about 8 dB improvement in Q factor and more than 10-fold enhancement in transmission reach compared to single channel DBP. Thank you for your attention. I will be happy to take any questions.
Thank you, Dr. Shivakumar. Any questions from the audience? Any questions?
Hello, sir. Enlighten a little bit on that virtual fiber concept, like realization of that. How do you realize?
Okay, good question. Sure, I will explain that. So what happens is that once we have this coherent receiver, the nice thing about coherent receiver is that we have access to both real and imaginary part of the optical field. So we digitize the optical field, whatever the output of this digitized form, we are going to get the complex optical field envelope is available here. And virtual fiber, if you look at the fiber, propagation in the fiber is given by this nonlinear Schrodinger equation. So this can be solved by something similar to the beam propagation method or split step Fourier technique or To realize dispersion, you use FFTs, and to realize the nonlinearity, you introduce a nonlinear phase shift. You have to do it with very, very small. For example, if you have got 80 kilometer length, you have to break into say 1 kilometer step size and apply dispersion, then apply nonlinearities after one after the other using FFTs. So in that way, but when you do virtual fiber, you have to change the sign of the dispersion, change sign of the loss, and change sign of the nonlinearity, everything. So you have to solve the nonlinear Schrodinger equation in real time on DSP unit. So that's what I mean by the virtual fiber.
How do we implement it in the system, sir? Means in physical system.
Okay, so what you do is that, let me suppose that the output comes in the digital form here. So if you are having an FPGA, that's a field programmable gate array, you are going to program it, just like you are going to program in MATLAB. If you want to solve the nonlinear Schrodinger equation, you write a MATLAB code, right? Same way, you program the FPGA to solve the nonlinear Schrodinger equation. Just realize FFT. You can realize FFT on FPGA, right, or in any programming. But it has to happen in real time. That is the only difference.
Oh, okay.
But that's why you have to have a very fast FPGA. People design something called the custom specific integrated circuit. So you have to use those ones which work at very high baud rates, at 28 gigabaud. People have realized it. So go on.
Okay. So, and we have to use it in a 1 kilometer interval.
I mean, you're not using it. You're using everything in one place. So what I said is that you can think that 80 kilometer fiber has got 80 segments of 1 kilometer. Think that for 1 kilometer, it's a dispersion in the 1 kilometer. You can remove the dispersion of 1 kilometer using one FFT. Then you introduce a nonlinear phase shift and remove the nonlinearity. Then comes to the second kilometer. Everything is sitting here in one place, not in different places. Okay. So comes to the next kilometer of the last span, for example, for which again introduce FFT, and again use remove the nonlinear phase shift. Like that, you have to run 80 times FFTs to remove the dispersion and nonlinearity of this 80 kilometer long this fiber span. So like that, you have to do for all the spans. So virtual fiber 1 for the nth span, virtual fiber 2 for the n-1 span, and so on.
Okay. Thank you, sir.
Okay, you're welcome.
So any other questions? Any other questions? So if there are no questions, I think now.
One second, Dr. Shivakumar.
Yes.
What perhaps is the status where people were talking about getting rid of electronic hardware and replacing with all optical systems, including signal processing, etc. Is that a reality?
It is happening, but it has been, we have been talking about it for more than 10 years or 15 years, and it's a slow progress, and some of the things can be done faster in optical domain. Some of the things can be done better in the electrical domain. So it is going to be a balance between the two. For example, FFT is done in the digital domain, but in optical domain, it can be done much faster with much larger bandwidth. So FFTs in optical domain has already a lot of work on that, optical signal processing using optical FFT, which is done using basically some kind of integrated circuits where you have got directional couplers and some kind of interferometers to realize the phase shifts. And just like if you remember the FFT in frequency decimation and time decimation, you can implement exactly those kind of FFTs using optical hardware. So that has, people have realized data rates of 100 gigabits per second using the optical for the optical OFDM system. So those things have been happening, and slowly it will. But what happened, one of the reasons why those things took a back seat, because the digital processing itself became faster. Since 2010, we are having very high speed DSP. So we can get like, even at 28 gigabaud, we can have DSP to operate. So that kind of lowered the speed of the optical signal processing, but it is happening. it will eventually, because the reason is that, as I mentioned, the optical back propagation is needed because it's too late to compensate in the digital domain, the non-linearities and dispersion. If you compensate in optical domain, you can get much better performance. So when there is a need like this, and if it cannot be done in digital domain, then people will start focusing on the optical.
Thank you. Thank you.
So any other questions? Because you can definitely, it's the right time to ask Professor Shivakumar, the participants who are doing research in, especially in fiber optic communication.
One more thing, sir. Sir, have you ever tried for no back reflection fiber? Means here you are talking about back means reverse transmission also. But anything like without back reflection, have you ever tried to make any fiber?
I mean, if you don't want any back reflection, you have to introduce the lambda by 4 plate, right? So you have to put this anti-reflection coating. So that is already commercially available. So you're talking about anti-reflection, right? If you send the signal to the fiber or signal to any device, you don't want any back reflection, right?
Yeah, at the interface. Yes.
So you have to put the anti-reflection coating.
Still. Okay, no, I was just wondering about now a new technology like that topological effect that gives no back reflection, means it's ideally zero back reflection. So any kind of technology like that.
Okay, I don't work on the device level, so I will not be able to give you the right answer on that. There may be some techniques, but I am not aware of that. I know the concept of anti-reflection, but I myself focus more on the communication side. So
yes, okay, thank you, sir.
So okay.
Any other questions?
So I think now I'll ask Professor M.E. Satyanarayana to have some discussion, one couple of discussion with Professor Shivakumar, then C.R. Nataraj, and finally T. Srinivas, and Matsudan will finally conclude.
Okay, sir.
Professor Satyanarayana, sir.
Sir, unmute yourself, sir.
Unmute.
Okay, sir.
Hello, Mr. Shivakumar.
Hello, Professor Satyanarayana. How are you?
How are you?
Good.
Okay, your lecture was very informative. So,
thank you.
Many compensation techniques you described. All of them are in operation now. This back pumping and things like
that.
The
research level. It's at the risk. I mean, the digital back propagation that is in the commercialized. People have been using for single channel, but it is not compatible with WDM. So that's why we are coming up with this optical back propagation. This is the research stage. We are doing experiments, and as I said, there are some difficulties with, and we are proposing newer schemes, and that's a research cycle. So it's not at the commercial stage yet. So it's in the research stage.
Okay, any potential development you see in the next 1 or 2 decades in optical fiber technology?
Good question. So next, what would happen is the multi-mode fibers. We have been thinking that multi-mode fiber is bad because it's too much highly dispersive. But what is happening is that in the case of single mode, it's from the information theory point of view, if you are going to have single mode, you are going to have certain capacity. If I'm going to have 2 mode, the channel capacity is doubled. So then if you are going to have 6 mode fiber, the capacity can be increased by 6-fold. So therefore, it is just like MIMO in wireless. So 6 mode fiber has drawn significant. It's also known as a space division multiplexing. So SDM. So that is going to have a big impact in the next 5 to 10 years. So, and also there will be some non-linearities among them. So it's So the main issue that people have demonstrated the space division multiplexing for short reach for 80 kilometers or less. But the problem is that when you're going to send 6 modes of fiber, each mode you are going to have its own information, say on-off keying, for example. Each of them have got 6. Their capacity is increased by 6 times. But the problem is, how are you going to amplify them? The EDFA is single mode. So you need to have the multi-mode amplifier. So that is the challenge people are trying to solve. So if that happens, if somebody can come up with an amplifier, multi-mode amplifier, I think that has got a very high potential in the next.
How the signals are supposed to be separated?
So you have to couple them together, all those modes. There's something called mode division multiplexing. You combine all these modes using mode division coupling. Dr. Srinivas can tell more about it. And at the other end, you have to do the mode division demultiplexing. So you have to use some techniques to the way in which it's exactly multiplex and demultiplex is going to be exactly the same. So.
Okay, thank you very much, Shivakumar.
Okay, you're welcome.
Professor Satnala, we have one student, Chandana from Ramaya Institute. She is working on this multi-mode communications. So we'll have some talk sometime soon after she finishes her thesis. We'll have a talk. And also we have another girl working on integrated optical devices for this MDM multi-mode.
Sir, you can switch on your video, sir. Your video is now.
Yeah, that's fine.
Okay.
So some work is going on, but of course the fiber optic is an experiment, but integrated optics is still theory.
Sir, that regarding the discussion, Professor Satyanarayan told how to separate the signals, sir. If you are multiplexing using the modes, that means each mode will be acting as a channel.
Yeah, I know.
Like LP modes. Ultimately, how do you demultiplex?
This is an idea. This is a very, somewhat the idea is there since some time. For example, you can use a directional coupler to separate out the input to the first port of the directional coupler. Of course, the mode, there should be 2 modes. And you can do some magic. You can manipulate and separate out first mode into first way output and second mode into second output.
Other arm of the directional coupler. So that's what you do.
Yes.
Now, one question So by using bireference, can you send 2 signals using a single mode fiber?
Yes. So although we say single mode fiber, it's not really a single mode fiber. It's bimodal. It's got 2 modes, right? HE11 and so what happens is that's what. So what was your question again? So basically, what we do when we call dual polarized communication, we send 2 modes of those fibers. So, but that's the problem is that there's a polarization mode dispersion or PMD between the two. The coupling between these 2 modes happens, and but thanks to the advancement in DSP, we can compensate for PMD at the end of the link on DSP unit. So we put a PMD compensation to undo any interaction between these 2 polarizations. But currently, all the commercial systems use dual polarized.
Okay. So I think with that one, I think finally CRN, process CRN. I think you can.
No, it was. I thank MCE for arranging a beautiful lecture by Dr. Shivakumar, and we also got to get in touch with Dr. Shivakumar after a long time. So I must thank the organizers and also for the excellent lecture given by him, particularly on the directions in which high-speed optical networks are moving in the background of non-linearities and degradations that would happen in the fiber for long-distance communication. Thank you.
Thank you, Professor Shiva. Sir, Professor Srinivas, sir. Finally your thing, Professor Srinivas, sir.
Sir, unmute, sir.
Sir, Professor Srinivas, sir, please unmute, sir.
I don't have any comment on the technical side, but I hope everyone knows that Shivakumar has studied in Hassan. You told them all, your students.
And
then, and then the other thing, IAS, of course, you told. Then the other thing is, I hope I will welcome everyone to the talk on this Friday. We have a talk in Kannada in photonics, so please join. So by Dr. Gopal Hegde, he is on Kannada. So you can please announce or show the slide. What is that called? The poster.
Yes, I have already communicated. Now once again I announce
it. Here itself you can show on the screen. You can share this slide so that people will know.
Shall I share, sir, now?
Yeah. Just now you can share for a minute and then you can close.
Yeah, I think I have to download it and share it.
Then I'll share just a minute if I have.
Yeah, you share, sir.
Should I stop presenting? Should I?
Yeah. Shivakumar.
Yes.
Dr. Gopal Hegde will be giving talk in Kannada on photonics.
Oh, okay. On photonics, okay. That's interesting.
And Dr. Srinivas has made every month one in different languages, like in Kannada, then next followed by Malayalam, that will be followed by Punjabi, like that.
That's nice. Yeah.
So Shivakumar, I think you may not be able to attend because it is sir, the timings easy. Is it
okay here? Almost at the same time. Now
I think you can attend, Shivakumar.
Okay, we'll see.
Yeah. You'll see the fragrance of Kannada and photonics. I think Srinivas will be presenting now. Yeah.
I just want to show people because most of them may know, but still. No, it is not coming. I'm using the cell phone, so I don't know how it comes. It should be open first of all. Anyway, I'll send it separately to everyone.
Okay.
Yeah.
Hello, sir.
Hello.
One more thing, like this separation of these multi modes, or separation of modes from a multi-mode fiber. Like, can we use a multi-core fiber at the end? Means splicing that multi-core fiber. Sir.
Multi-core fiber cannot be used for mode division, demultiplexing or multiplexing. Multi-core fiber itself is another way to increase the capacity.
No, sir. I am saying like we have to define cores like with a threshold, like it will accommodate. Suppose for fundamental mode, the core diameter will be separate. For the second higher order mode, the core diameter will be separate. So fundamental mode, which will be come out of each core, will have a different. If we combine all those, then we'll have the 6 modes.
Okay, there is a problem with what you are saying. I will tell you the problem, because if you are going to have, let's say that your fiber core is say only
8 micron.
8 micron, for example.
Yes.
Say 4 micron. Okay, core radius.
Okay.
4 micron. Then it's single mode. Sure. And if you make it 8 micron, there's a chance of having a second mode coming in. So first mode and second mode. If you make the 10 micron, for example, it will have first, second, and third modes, and so on. As you increase the core size, you are not just getting the second mode; you are getting all the modes from first mode.
Yes.
So
but then we could take only the higher order mode from that. We'll leave another mode.
Let us suppose that we have got like 6 modes coming from the transmission fiber, and what is your proposal to have a multi-core fiber with, say, the smallest core, of course, gets the fundamental, sure. Yes. How do you get the, say, 6th mode out? It cannot be separated out, right?
Okay, we need not to be, okay. So in that case, cannot we take only the higher order mode from that core, from the, means if we have 6 cores, we have to take only one mode from one core. So
no,
is it not possible?
How do you separate the 6, the higher order? You can separate the lower order mode easily, right? If you have a small core, lower order mode can be, but the higher order mode cannot be separated that easily, because that if you make the diameter larger, it supports many modes. So
yeah,
it's
that
not
will
only
come.
supporting
Yes, that is in my mind, but I thought maybe taking means
there are
taking
other
up.
things like
Yeah,
that you can use a directional coupler and play with
yeah.
some gratings you can use. And
No, for when we increase the mode number up to 6, then that will be a problem. Now, even using directional coupler and.
I mean, when we say 6 modes, it's not really 6 modes. What happens is that you use fundamental mode, which has got X
Yeah.
and Y polarization. Then the
Yes.
third or second mode, which also has got X and Y polarization, like
Oh,
that. So it's
okay,
actually
okay. I understood, sir. Now.
I think now you can see the talk. Professor Srinivas has already presented. Is presenting. So it is under Prakash Bharathi, IEEE Photonics Society, a network of photonics professionals of India. I think, are you seeing, sir? Sir, it is visible. Yes, sir.
It's visible, sir.
I can see that, yes.
Sir, it is visible, sir.
Yeah, I can see it.
Yeah, we are seeing it. So probably I think Shivakumar, you can read, no?
Yes, I can read. Gopala Krishna.
It is readable. Anyhow, I will be sending you.
Okay.
I am sending you the link. I think
so
you
is
can.
Dr. Hegde is with you, Srinivas? He's in your department, or?
He is muted. He is in sense department, that is nanoscience department.
Oh, I see. Okay.
Sir, Professor Shiva, sir, please unmute, sir. So he is trying.
So he is there in the Department of Nanoscience and Engineering, and he is an experimental person specializing on lithography.
I see.
So he was there with our group since long time with Professor Salva. He was there in Singapore for some time. Then he came back to India.
I see.
So now he is very active in all these things.
Sir, with all that, shall we conclude this one?
Sure.
Shivakumar, okay.
Yes, please.
Yeah, Shivakumar, definitely it's really a wonderful and more informative talk from you. And we know how you can even you are thrown light on spatial division multiplexing at the end also, and also bimodal fibers, and also before that one you have done completely about fiber impairments, and very informative, and I think most of our research scholars have gained from this one. So with that, once again I would like to thank Professor Shivakumar on behalf of Prakash Bharathi. Shivakumar, we have got Prakash Bharathi India, and I request you to become a member, WhatsApp member. I will add you to Prakash Bharathi. Today, I think I'll be adding you. That's why I asked you in the WhatsApp, but you have not given me the answer. Today, I'll be adding you. Okay. It is a very good group. And now it is headed by Professor Srinivas. He is doing excellent work. And we have got most of them are NRIs, like Shivakumar, like you, and Naresh and Nilay, many are there. And of course, many of them are from India also. So it's a very big group. Now it is becoming a very big group. So I really invite you to our Prakash Bharathi, and most of the Indians who are staying in abroad, they are actually telling that we should do something to our motherland. So that is what they think they are telling after staying in US or UK or Canada for more than 2, 3 or 4 decades or 5 decades. So they are coming up. So we want to do something for our motherland, and some professor like Naresh told that we can give even blood also. He was telling like that in the group. So it's a very nice group, and also I have already told Professor Srinivas is heading that group. Of course, it is first of all founded by Dr. Naresh only, along with me and Professor Srinivas when we were there in IIT Guwahati. So with that one, definitely under Prakash Bharathi, we are doing very good programs, and it is growing. And also we need some experimental things that would be helpful for our students from your side, Shivakumar. I think we need your help in developing the relationship between Indian universities and abroad, so that they can do virtual, at least at this point of pandemic. And another thing is definitely I would like to really thank Professor Srinivas, Professor Satyanarayana, Professor C.R. Nataraj. They are really backbone behind us. Even now they are doing excellently well in their field, especially even after retiring Professor Srinivas and Professor C.R. Nataraj. They have shown interest, and definitely every day they are actually updating their knowledge. And also I would like to thank our institute that it is joint venture from it's good that it's a joint venture from Malnad College of Engineering, Hassan, and Calcutta University, Calcutta. So from Calcutta University, I would like to thank Madhusudan Mishra. I think Madhusudan Mishra.
Sure, thank you, sir.
So you have done excellently, very well organized this webinar, and also he is one of the organizers. I would like to thank all my student friends who have organized. It's a student activity. It is done by, first of all, from Calcutta University, Madhusudan Mishra, from our college, Yashaswini, Vijay Kumar, then Rachana, and then Pooja. So they have worked very hard to come to doing these kind of webinars. And also this is the third seminar in the series we have done, the webinar or seminar. And most of them are from fiber, optic fiber communication only. Starting with Shivakumar, she gave. Today I thought she would join, I don't know. So with all that one, I think, shall we leave for now?
Thank you very much for inviting me, and it was a pleasure meeting all of you and getting reconnected with all of my former friends and Professor Satyanarayan, Nataraj, Dr. Srinivas, and Shrikant. Very nice meeting you, all of you. Thank you. I'll be glad to